Bismillahirrahmanirrahim. Today's topic is two-dimensional or planar trusses. First, we start with some definitions or some limitations. We'll be dealing with pin-jointed elements. Elements will be joined with pins. There's no welding involved, and which means that these are axial force members. If I borrow a term from mechanics of materials, these are two force members. So each member of this truss is a two force member, and therefore there is no bending involved. The forces have to pass through the axis of each member, and the forces are applied only on the joints. There's no provision of force acting here, because if the force acts here, then it's by definition it's not a two force member, and then there'll be bending involved and all that sort of thing. We have elements to deal with that, but here we have limited our analysis to these conditions. Now, the good thing is that if it's an axial force member, then we know the equations for axial force. For example, we know that for any axial force member, this is the member which is subjected to this kind of force or compression, either tension or compression, which each of these members will be subjected to. Then the K matrix for this, should be very familiar by now, is nothing but this. So we have already got a start in these problems. But there's another factor which we have to consider, and that is that we know the equations, that's all right, but some sort of transformation will be needed. Let me explain this one. If we take this as an x-axis, then this is perfectly legitimate expression for the stiffness in this member. Similarly, if we take this member, this member is this one. If we take this member now, with this x-axis, the same applies here. Obviously, this may have different values for A, E, or L, but this expression is still valid. So for all elements individually, this expression is valid as long as you align your x-axis, your main axis, with the axis of the element. Now, if you assemble or if you derive the stiffness matrices for all these by changing the x-axis respectively for each member, how are you going to assemble them together? Because there will be no way you can assemble different systems together, different systems which have different orientations, different coordinate systems. So we need to have, first of all, we will basically establish a global coordinate system. These are local ones. This local coordinates. This is another local. So you'll have as many local coordinate systems as you'll have the members in your system, but we will need a universal system so that each quantity is derived in that, and then it will be possible for you to assemble them together because the currency will be the same. So let me write here. We will come up with, obviously xy, we are familiar with this, local coordinate system for each element. These will be different for the different elements, but here we introduce global coordinates. Which will be universal for all elements of the system. So our global elements will be, this will be constant for every member. Obviously, for individual members, the local will be changing depending on its orientation, but the global will be the same. Let's start establishing the relationship between the global and the local coordinates. Because first of all, before assembly, we'll have to convert all these local coordinates, all these expressions in the local coordinates into global coordinate system so that we are able to assemble them all together. But later on, after solution, because stresses and strains are local phenomena, stress in this member will be in this direction, strain will also be in this direction. In this member, the stress and strain will be in this direction. So there the global will not be of much use to us. So once we have figured out the displacements in each joint after solution of those equations which we have assembled, and for assembly we need global currency. After that, we again shift back to the local coordinate system where we figure out the strains and stresses. So this transformation is basically what separates us now from the solution of this, because we know the starting point. We are familiar with the equations for these elements one by one, but because we have to do transformation first into global and then later on into the local system, so we need to derive those laws of transformation. Let's see how they look like. Let's say we have this element, and the element is, let's say, in this orientation. This is the orient. We have just talked about the one-dimensional elements. Let's say this is I node, this is J. Every element is like this. It has some orientation and it has two nodes. So let's say an important point here is each of these elements are 1D systems. This is a 1D thing. This is also a 1D thing. This is also a 1D thing. But because we have different orientations, if they were all in one line, all oriented towards the x direction, then it would be a 1D system. But because all have different orientations, therefore this system is a 2D system, hence the word 2D here. Individual elements are 1D, but because they are aligned in different directions, we also have to consider the second dimension. So it's a 2D system. Now, if this is J node, let's say this is the J node, and I node will be somewhere here. So now, let's say this, after deformation, after displacement, you apply the loads, and this is the displacement. The J point moves from this point to this point. Let's take this as our origin. This ij element, I was somewhere here, this ij element. Now after the application of forces and the new equilibrium position achieved, it now comes here. So this, from origin O to this point P, this is the displacement of this J. Now we can obviously start our transformation from here. This is the global x-axis, this is the global y-axis, and the axis which is parallel to the original orientation of this is the local coordinate system, x and y. Y is always at 90 degrees to x. So this x, y, this is the local coordinates, and these x naught, y naught, these are the global coordinates. Obviously, for every truss element, it could have different orientations, so you'll have different x and x, y's, but x naught, y naught will be the same. And one thing that is always constant is that x and y, similarly x and y, they are at 90 degrees, and we are following the right hand coordinate system, right hand systems. So let's see what we get as the components in these two systems. Now this is u naught, this is the displacement in the x direction, and we are talking about the x naught, so u naught in the global system, and this is v naught on the y-axis. This is the component on the y-axis. Similarly, this is the u component on this axis, x axis, and on the y-axis this will be the v component. Let's say this is the v component. These are the global, these are the local. Now let's say that the original angle of this element was alpha. Now if this is alpha, then this is obviously beta. So now we can now start our transformation. This one, this bold line, this is nothing but u I'm sorry, this one, not this one. This one is nothing but u naught cos alpha. Please ignore this one. Now what about this one? Obviously this is u naught sin alpha. This is u naught sin alpha, this is u naught cos alpha. Similarly, this one, this in bold. Now this is, because if this is alpha, then this is also alpha. If this is alpha, then this is also alpha. So this one is v naught sin alpha, and this one here is obviously this is v naught cos alpha. Now it's very easy to see that if alpha plus beta is equal to 90 degrees, if it is the case, which is the case here for us, then we know that it's simple trigonometry. Sin alpha is equal to cos beta, if this is the case. So wherever we have sin alphas, we can convert them into, it's the same thing. It's just, we are just simplifying. We are just taking one thing out of the equation to make it simpler. And there's also another reason which we'll come to later. Similarly here, this is nothing but, now if you see what u is, now we are ready for our transformation. U, this u, this u, this is nothing but this plus this, this plus this. So we know what is this and what is this, so we can write that u naught cos alpha plus v naught cos beta, I'm sorry, this plus this. Similarly v, this is v, this is v, v is this minus this one minus this one. We know what this is and we know what this is, So we can again write it, and just to be consistent we can rewrite it minus u naught cos beta plus v naught cos alpha. And why we do this is, now it's very systematic for us to write this equation as so this is the transformation. We were interested in transformation because at least on two occasions we need to shift from the first we shift from local to global and then back to global to local. So we have started on that path. Now this cos alpha, these are nothing but direction cosines. For any line you have direction cosines. For 2D system there are two, and for 3D system there are three direction cosines. So here cos alpha will be called L, which is a convention. Cos beta will be called M, and this is why we transformed this from sine alpha to cos beta, because we wanted to ultimately use the direction cosines, which we cannot use directly with sine. And in 3D what we'll do is simply add to cos alpha and cos beta, we'll add something else, cos gamma, that's all. With cos and sine we are stuck there. So with causes you have three cos, and for 3D system you need three direction cosines. So with this kind of nomenclature it's very easy for us to extend this to three-dimensional cases. So putting these values here back to Lm minus ml, now this is just for any vector OP. In this case it was the displacement of the J node from the origin to some new place. But if you consider that each truss member has two such points, two nodes I and J, obviously, and I and J both transformed by the same transformation equations, so we can extend this to a system with two nodes. And obviously we don't need to derive that again because we have already done the derivation. The second point should also transform in the same way. But now here we have UIVI, UJVJ, because there are two now. For UIVI we already know what the transformation law is, Lm minus ml. Here also you will have the same law, don't need to derive all over again. Here we have zeros, we don't need any values here. And on the right hand side, ui naught, vi naught, uj naught, vj naught. This was the original equation, u naught, v naught, because we are just talking about this one point. Now you have I node and j node, both will transform in the same way, so we have to differentiate between I and j, and also we have to increase the size of the K matrix appropriately. Now let's call this U, symbolically U. Let's call this matrix lambda. Let's call this U naught. Again, naught will, this circle, this will signify that we are talking about the global system here. Now if displacements are from local to global, or in other words from global to local, if they are transformed using this lambda, it's very easy to say, and it would be correct to say, that forces, which are also vectors, because this transformation is vector transformation, it doesn't matter what vector it is, whether it's a displacement vector or a force vector, both should transform with the same equations. So we can also write it like this, because there will be forces also in the global system and the local system. So if I, just for completion's sake, F, where F is equal to Fix, Fiy, fjx, fjy, talking about these are the local forces in the local coordinate system, and f naught, fix naught, fy, fiy naught, fjx naught, fjy naught. These are the global coordinates. Now we are very familiar with this equation in all FEM problems. Ultimately we get this solution. What sort of shape this takes, obviously it depends on the problem, but this F is equal to KU, this is basically the equation for a spring. And all systems, ultimately when you talk about stress analysis problems, especially problems where we are not talking about we are just talking about equilibrium problems, we are not talking about dynamic problems, then this is the shape. So if we put the values here for F, we and K comes as it is, and for U we again replace the values from here, then the equation for this, for global, in global coordinate system, the equation will basically become this. So this means that this quantity is nothing but the K in the global system, because F is equal to KU. In this case, this is K naught. So this is how we transform the K matrix in the local system. We know this is the expression for K matrix in the local system. We just multiply it from on both sides with the lambda, this matrix. Here it's the inverse of lambda, here is the lambda itself, and what we get is the K naught, which is the global. So for every element we have to convert that element from the local to the global system. Then we'll do our business, assemble them, solve them, and at the end we'll just go back and we'll deal with that when we come to that point. Now an interesting thing happens here. This lambda is one of those matrices. It turns out that it's an orthogonal matrix. And what is an orthogonal matrix? An orthogonal matrix is that in which the transpose is equal to the inverse. And this makes life much easier for us because it is very easy to take the transpose. It takes a lot of time and effort to find the inverse of a matrix, but in this case both are the same. So we can write this equation as transpose K so now finally this is also correct, but as far as we are concerned now, this will be the F matrix in the global coordinate system. This is the equation, FEM equation in the global coordinate system. In global coordinate system, where K naught, and we have to do it for all the elements, where K naught will be and this K is in local, and these lambdas, they will depends on orientation of the element of each other, because with orientation L and M will change. This is our equation for the transformation. Now there's just one more thing to do here, and then we can move on to our problems, and that is that it's very important to recall that please recall that in the local coordinate system, Vi and Vj are useless. Why? Let's see. If this is our x coordinate system, locally we will just align our coordinate system with the orientation of every element. So let's say this element is at an angle theta. We orient our local coordinate in that direction also. So here this displacement is of importance because it is either stretching or it is contracting. But if it moves in this direction, obviously it will just be a rotation. It has nothing to do with the stretch or elongation of this element, because it's, remember that it's a linear element, axial element. So there's no this deformation perpendicular to its axis. All the deformations are in the axis. So any force, meaningful force, is also in this direction. Any displacement is also in this direction. Forces and displacements in this direction are meaningless here. So while when we started, said that this is the original orientation. Now the final point where this node J rests is this one. So this has a U and V component, but this V component is just change of orientation. It has nothing to do with the stretch or contraction of the body. So if this is the case, then it's very easy to say that this Vi and Vj are not needed by us. They are basically, these are, as far as our analysis is concerned, we don't need them. They are not actually there. So we can just write this equation, the same equation, by removing these lines. Simply remove these lines. So we get Ui, Uj. These are important, Ui and Uj. If there's Ui here, Uj here, and Ui here, this will decide what sort of strain is there and then what sort of stress is there. Vi, Vj are irrelevant. So we just make our lives a little easier by just removing those two lines. The right hand side remains the same, because remember, in the global coordinate system we need all the four components. Whenever this a new location, it moves to this location. So this sort of UIV in the global coordinate system, this is the x naught and y naught system. Motion from this point to this point involves all the four. It could involve all the four coordinates, but when it comes to locally it's either a stretch or a contraction. So we don't need the v direction. So this is the distinction that needs to be made here, and it makes life easier for us. And if we now go back to this equation, how to calculate from local coordinate system your k, which is very easy. We know AE over L 1 minus 1 minus 1 1, and how to convert this using this to global stiffness matrix. It's very easy. Just put in the values here. We have to use the first we have to use the transpose of this thing, and that is LM0000 LM. Then we need to use the k in the local system, AE over L 1 minus 1 minus 1 1, and then we have to use the lambda again, LM0000 LM, which comes out to be, if we solve this, then this results in k naught. Remember that this naught is for global. This is AE over L, that is the same, but now L square M square L square M square LM minus L square minus LM minus LM minus M square LM. And here we have, obviously it's a symmetric thing, so this is here M square. This is the K matrix in the global coordinate system. For each element we have to come up with this one, and then because this is in global coordinate system, so each element will be in global, so it's very easy to add them together using the connectivity table. Again, use the connectivity, and here we can use it, assemble using the connectivity table. If it was in this form, local, how can you add an element in this orientation to an element in, let's say, this orientation? These are completely different coordinate systems. There is no basis for addition. Here we have the basis for addition. Now, one more thing, and then we can go on to the problem, and that is, it's very easy to find out the values of L and M without going into cumbersome calculations of theta and using sine and cos and all that sort of thing. Obviously that is not wrong either, but if you have ij node, 2 nodes, and the global coordinates of those nodes are these, so it's always easy to write your I and j in terms of global coordinates, even if you are given lengths of them and or angles. Once you write them in this form, then the length of the element is nothing but simple trigonometry will tell you that and L and M are even simpler. This is how you calculate L and M. Once you have L and M, you can just, and A, E, or L, and L will be given in the question in your problem, so it shouldn't be a problem. So this is the way you do the problems. But there's just one more point that we need to get out of our way, and that is about the forces. We have figured out how to calculate the K matrix in the global coordinate system. What about the forces? Now, it's very easy to apply the forces as far as the nodal forces are concerned. For example, if there is a because nodal forces are usually given in global coordinate system. For example, this is an element here, and you are given these forces. So simply this is whatever the degree of freedom is. For that degree of freedom, you apply this force. These are already in global. If they are given in this form, they are in global coordinate system. But if they are, let's say, given in this form, some sort of angle, then you can always calculate these. So it's very easy to apply the concentrated forces on the right hand side. But are there any other forces that are applicable in this case? We know of concentrated forces, we know of body forces, we know of pressure forces, and then thermal forces. Now, pressure forces are again not applicable here because it's a pin jointed thing. Here there will be another element. The only way, legitimate way for this analysis is to apply the forces by using these pins. So pressure forces are out, so we don't need to worry about them, because if we include them, then our initial assumptions, they are violated, so this analysis is not for them. Similarly, body forces, this has some weight also. If we say that this is being pulled down by its own weight, again it will cease to be a two force member. There will be bending involved here and everything. So again, this violates our basic analysis assumptions, so these are not there. But what about thermal forces? There's a temperature change, delta T, and because of delta T, each element increases in length. That is very legitimate because that increase in length, that will be in axial direction, and some sort of force will be applied on these points because of the pins. That will also be in axial direction because again it's a two force member, only two pins are there that transmit forces. So this one is valid. So I'll just spend some time regarding thermal force vector, how to calculate the thermal force vector for our problem. So we'll just have to go back to our original this is the one. For this we have to again come back to our original transformation equation. This is the way you transform from global to local using the lambda matrix. Now if I can write this again in terms of forces, now again we're talking about forces now, but we have already mentioned that this transformation is not for displacements alone, this is also for forces. So if we rewrite this again in terms of forces, I'm just replacing local displacement by local forces, and I'll replace global displacement by global forces. That's all. I'm not going to change anything else because the transformation that doesn't change. LM00, please recall, minus ML00 LM00 minus ML, and here I'll have the same values but in the global coordinates. Now in a similar way like we did last time, we had said that these Vi and Vj, they are not relevant for us because in the local coordinate system, any element only extends or contracts in its original coordinate system, it's in its local coordinate system. There's no perpendicular extension or anything like that. If there's a motion, then that is just a rigid body motion, just change of angle. It has nothing to do with stresses or strain. Similar is the case with the forces. If we had taken these two out as irrelevant, we can also say that Fiy and Fjy are irrelevant too. But let's first of all transform it from one to the other, because here we need to find out this. So we'll just transform it, take this to the other side. Now taking this to the other side means taking the inverse of it, but in this case we know that it's an orthogonal matrix, so it's just the transpose will do as well. So this is equal to, simply take the transpose of this, L minus M L. This is the way you take the transpose, which is also the inverse, and in this case Fix, Fiy, Fjx, Fgy. Now in this case these are irrelevant, and if these are relevant, then again in this case there we had got rid of two rows, here we'll get rid of the second and the fourth column, because those are the things that are being multiplied here. So I can just write it F naught, I'll just write it thermal here, let's specify thermal here too, and it will be nothing but L0 M0 0 L0 M. I've just taken these two columns out, and here I have Fix and Fjx. Now this is again thermal in local coordinates. This is thermal in global. Now what do we know about this, which is nothing but thermal? What do we know of the thermal force vector in the local coordinate system? That's very simple. E A alpha delta t minus 1 1. You should recall from your 1D analysis, this is what it was. So we know this value. We just put it here and thermal L0 M0 0 L0 M EA. This part is the local coordinate system part. This should get us the global minus 1 1, which turns out to be minus L minus M L and M. This is how you deal with the thermal force vector, and this is the only vector you are going to deal with as far as force is concerned, because the concentrated force vectors, they are very easy to apply. You don't need to have an equation for them. You just apply them as and where they occur. As far as body force and pressure forces are concerned, they are not relevant for this kind of a problem. So here what you do is you just use the K matrix that you have derived, and then you just apply this equation and get your, here you have, for the K matrix for individual elements you will derive this K matrix, because this will be in global coordinate system. For thermal vectors, if any temperature changes are there, you apply this is in global coordinate system. Then you assemble all the other elements to assemble them into one whole system. You get the system matrices. Then you apply any concentrated loads acting on the body, you apply them at the end. Then you solve the problem, and once your problem is solved, it means that in the global coordinate system you'll get the displacements. Once you get the displacements, then all you need to do is go back to your local system, because strains and stresses will always be considered in the local coordinates. There is no meaning of a strain for this kind of an element, this element oriented in this direction. There is no meaning of strain in this direction or that. Strain for two force members is in the direction of the member itself. Same goes for stress. You do that. And one thing you need to always remember, again, like we did last time, that whenever there is a delta T involved, there's a change of temperature, and then there's a force vector because of that. The displacements you get, they are the total displacements, and because of the thermal as well as the mechanical part. So the strains calculated will be total strains. You have to subtract the thermal strains from those values to get the stresses. We'll deal with that when we take up a couple of problems using the theory that we have just derived. Thank you very much.